Okay, this lesson, our objective is to use combinations, whereas in section 12.1 we use permutations, not objectively, objective, and use combinations to count. So these are still counting problems, but now we're using something called combinations instead of permutations. Now, why would we do that? Well, combinations. Before, when we were working on permutations, we were counting events that happen where order uh, like order mattered. So like when we say how many different license plates can there be, for example, where the number of where the number of letters is, excuse me, um, or if we have like how many three-letter combinations are there? Like APX is different than XPA, is different than um, PXA. So all these different things are different, and so when we count all the letters things, we want to count all of those possibilities. So 26 times 26 times 26, or if there's no repetition, 26 times 25 times 24. But in those problems, order is important, so we want to account for all these different orders. But if I'm talking about that's permutations. But if I'm talking about that was last section. If I'm talking about combinations, I don't care about order. Let me give you an example why I wouldn't care. Let's say I'm talking about pizza toppings. Let's say I'm at a restaurant and there's 4 possible pizza toppings: sausage, pepperoni, mushrooms, and olives. Now, if I'm talking about, let's say I want 2 topping combinations. I have SP, but I also have PS. Well, that makes no difference. Sausage, pepperoni, and pepperoni sausage, it doesn't matter the difference. And so I would want to divide by 2 to take those 2 types of 2 topping things out of the equation. So basically, this is very similar to the type of problem we were looking at before when we were looking at letters that repeat in a word, like when I have the word cheese, and I want to take out, all the e's that are, there's how many possible combinations of e? Well, E1, E2, and E3. If it's like E1 is red and E3 is yellow and E2 is blue, or something like that, then there would be 6 different combinations of this. 3 factorial equals 6. 6 different permutations of these e's. But since they all make no difference to me, I don't care about them, so I divided them out to come out with the possible ways to scramble this word. So the answer for the number of possible ways to scramble the letters in E was 6 factorial for the 6 letters in the thing, divided by 3 factorial because there's that many repetitions. So that was still permutations with repetition, but combinations is like that. Combinations. So let's say we're talking about 4 topping pizzas, and let's say, or there's those 4 possible toppings, and we're talking about 2 of them. So what we would say is like, how many 2 topping combinations are there? So we would say 4C2. That's how we denote that. Now 4P2, we remember, 4P2 would just be 4 times 3, right? And that gets me 12 possible combinations, and I'll show you. So I've got 3 types that start with sausage, 3 types that start with mushroom, 3 types that start with pepperoni, and I've got 3 types that start with olive, right? This is also similar to the problem where I told groups of 4 if you're in a group of 4 in your class, how many fist bumps are there in the group? Well, each group member could fist bump 3 other group members, and so that would seemingly be 12 fist bumps. But that would be 12 permutations if it mattered who was, like, if one person was fist bumping the other, and it mattered which one was fist bumping which. But order doesn't matter, so we have to eliminate the repetition. So OS and SO are, so I'm going to eliminate that one. OP and PO, so eliminate that. OM and MO, eliminate that. And then we've got MP and PM, so I'm going to eliminate that. PS and SP, so I'm going to eliminate that. And I should have one more I can eliminate, and there it is, SM and MS. So I've got 6 left. So I had to divide by 2, and what am I really dividing by is 2 factorial, but it just so happens that it's 2. Let me give you another example. How many 3 topping combinations are there? So 3 topping combinations, permutations for P3 would be 4 times 3 times 2 is 24 possible 3 topping combinations. And let's look at them. Okay, now we have 24 permutations, but again, repeat. So now there's, for every a 3-item combination, there should be 3 repeats. So PM. So I'll start eliminating repeats here, and I'll see them within the same. Like every single one in here is repeated. So POM, POM, PMS. So now I'm down to 12, and then I think I still have some more repeats. Like POM is here, but it's also up here. So there it goes. PMS, PMS, SOP, SOP. And there is OSP, OMS, OPM, OPM, SMO, SMO. So you see, ultimately, there end up being just 4 different ones. Because there's only 4 things. If you have 3 toppings, there's really 1 topping missing in each one. This one's missing olives, this one's missing pepperoni, this one's missing mushrooms, and this one's missing sausage. So you're down to 4. So you took your 24 and you divided by 6. So that's how combinations work. Permutations is, so if you take your 4 toppings, your permutations for P3 equals n factorial over 4 minus 3 factorial, or just 1. But take 4 C3, so this one ends up being 24 up here, right? But this, you take your n factorial, but you divide by, not only do you divide by the 4 minus 3, but you also divide by this factorial. So you call that r factorial. And in fact, the longer formula is written out are these. And notice, so C is going to be a smaller number. And in this last case, permutations was 24, but combinations was only 4. Because in both cases you divide by this to account for the fact that you only care about the number that you're taking. So you take 4 times 3 times 2. But then here you divide by the actual r factorial to divide out all of the repeats. So divide that out and you get just 4 as your combinations. Okay, so what that can lead to is this sort of an interesting thing that happens with that. So finding combinations for this pizza example, we're gonna build something. So if I have four toppings, if I have 4 toppings I'm choosing from, then and let's say I want a 4 topping pizza. How many different types are there? Well, there's 1, right? 1 type. If I want a 3 topping pizza, how many combinations are there? We just figured out there's 4 combinations. If I want a 2 topping pizza, so and what have I decided so far? So 4C4 is 1, 4C3 is 4, 4C2. How many 2 topping combinations are there? Well, that would be 4 times 3 on top over 2 factorial. So it's going to be 6 because 2 factorial is just 2. So basically it's 12 this is like the fist bump problem. You know, there's 6 two-topping combinations. How about 4C1? How many one-topping combinations are there? Well, you know, you have 4 choices. Well, there's going to be 4 then, 4 choices. And what about 0-topping combinations? 4C0. Well, that's going to be 1. Now, what if we were talking about 3-topping pizzas? Well, 3C3 would be 1. What about 2-topping combinations out of 3 toppings? Well, let's say we have mushroom, sausage, and pepperoni. Well, there's mushroom, sausage, sausage, pepperoni, and mushroom, pepperoni. There's 3 possibilities. What about 1-topping combinations? Well, again, there's 3 possibilities: mushroom, sausage, and pepperoni. And 0 toppings, there's always just 1 of those. How about if we had only 2 possibilities: sausage and pepperoni? 2-topping combinations, there's just 1. 1-topping combinations, there's 2. And 0 toppings, there's 1. What if I only had 1 to choose from? Well, there's 1 type of pizza with 1 topping and 1 type with 0 toppings. And if we're talking about 0 toppings to choose from, there's only 1. And what did I just make? This is called Pascal's triangle. And what happens if you look at it, I mean, you can make it from laying out C like this. This is explained better on page 710 in your book, or it's laid out for you visually better. But what you notice in Pascal's triangle, you can derive it from these, but you can also figure it out just by looking at patterns. Like you can notice, for example, that the 1 is going to come down the left and the right, and then this number just is going to be 5, 5, right? Because it's just the number 2, 3, 4, 5, so that with that row. But you also start to notice that this number, every number in the triangle comes from adding the top 2 above it. So this is going to be 10. This is going to be 10. And it moves on like that. So it's got some interesting properties, we'll say. And one of its interesting properties is that these numbers happen to be the coefficients of what happens when I square take a binomial to that power. So like remember these for a minute. And if we jump to the next page, if I take x plus y squared, I'm going to get x squared plus 2xy plus y squared. So what are the coefficients? 1, 2, 1. If I take x plus y cubed, I'm going to get x cubed plus 3x squared y plus 3xy squared plus y cubed. What are my coefficients? 1, 3, 3, 1. So figuring this out, you can start to figure out that x plus y to the 4th is going to be 1x to the 4th plus 4x cubed y. And what's happening? The y power is descending by 1. The x power is the y power is increasing by 1 as we go from left to right. So each term, my x power goes from 4 here to 3 to 2 to 1 to 0. And then my y power starts at 0 and goes to 1 to 2 to 3 to 4. But the coefficients are from Pascal's triangle. And there's some difficult problems that can be assigned to you that rely on this fact. And it can also be given to you as the binomial theorem. And it can be written out in a very complicated way, but I think this is really the simplest way to look at it. Okay, so we'll do some problems in class tomorrow. Thank you for watching.